Hi, welcome everybody to this nice rainy afternoon. So, announcements, as always in the beginning. Final project groups are due today, so please don't forget to register. I had at least one email of a student who couldn't find a group. If that is the case for you, please fill this form out anyways, mark other team members as X's, so that we are aware that you still need a group, and then we're going to assign you guys most probably to a group. So please register today. The deadline is today. Then homework 4 is out, and there's been a slight correction to problem 2a. If you download this now, it's all fine. If you have already downloaded it, there's a post on Piazza with the correction, so please have a look at it. Oh, I thought I took that animation out. So short recap from last Tuesday. We talked about decision trees, and this was the main idea, right? You grow your tree here, and you build these rules. You split on single features, and you have a threshold for each feature, for each split. And the result is that you split your feature space into these cells, basically. And then the prediction afterwards works in the way that if you get a new data point, it is in one of those cells. And you get there by traversing the tree. And then if your data point ends up in cell B, you look up the class for that cell, and that is assigned to that data point. And just to get into things again, I wanted to have a look at the signature of the function in scikit-learn. So when you want to train a decision tree, this is the scikit-learn function you can use. So you have this object under sklearn tree. There's this decision tree classifier. And I just, as a recap, wanted to look at the default values here for all those parameters in there. And you can see it's already slightly more complicated than the k-nearest neighbors classifier. If anybody of you ever looked at the definition of that one, only had 2 parameters. So you have here your split criterion, and it says Gini. And if you remember, there was this node purity measure that we talked about, right? So the other choice that you have here is entropy. And I said, in praxis, I haven't used those that much. Most probably it's a parameter you can just tune with cross-validation. Just try which one works better for you. So, and then this is interesting. There's a splitter parameter, and this is called best. Best is the default for the decision tree. It means it looks at every feature it has, and for each of these features, it computes the best split, right? And then looks at the highest purity gain for any of those. But for each feature, it tries to get the best split, and then it takes the best feature with its best split. And the interesting part is that you can have 2 options here, and the other option is called random. Here you can choose best, or you can choose random. And random chooses the best random split. Any ideas what that means? Because I have a very good guess, but I'm not entirely sure. Is anybody completely sure what this means? No. Can anybody guess what that means? Splitter. Random to choose the best random split. What could that mean? What could be random here? Yes?
Is it possible that they just randomly choose one of the data points as a criteria to split the data?
I don't think it's one of the data points, but it does choose one thing at random. The boundary, yes, in the sense, I think it chooses the threshold randomly. Because so instead of optimizing the theta, the threshold, right, this guy here. Instead of optimizing this theta, so my decision boundary here, on its best place for that feature, it chooses a random threshold. Right? And then you just have to, for each of the features, it just chooses one random threshold and then takes the best of those. And of course, that might be not the best one, right? If it would have optimized the threshold, most probably would have gotten a better one. This seems to not make sense at the moment. Why would I train a tree that has randomness in it, and for that matter, most probably doesn't perform as well as one that I would have optimized, right? It sounds kind of crazy, but there is sense to this, and we're going to see this because this is important for the ensembles to perform better. You want randomness, you want your trees to look different, and these are ways to achieve that. So this is my best intuition also. I believe it chooses a random threshold, and then for these random thresholds takes the best feature. And there's another one, max features. That is also important to think about. This is again about randomness. Yes?
How does the algorithm define the best? Is it the local best, or the local best doesn't mean the overall best?
It's your criterion that you give here. If it's Gini, it's this node purity it looks at. It's the max gain here. So maximum number of features. The default, if you put none here, is to use all features in there, right? Because you want to optimize over all the features in there and take the best split. Now we already said we can choose the threshold randomly. And here's another option to introduce randomness into a decision tree. And it's to only look at a certain number of features at a subset. So I know my digit data set had like 64 dimensions, and I say you're only allowed to look at 20 of those. And you can randomly select which 20. So what that means is when I grow my tree here, for the first split, it only looks at 20 features, randomly chosen out of those 64. From those, it chooses the best split. And then for the next split, it again chooses 20 different, not necessarily different, it just again chooses 20 random features out of the 64, looks at those. Right? So I again get a tree that learns something that is optimized to a certain degree, but it's not as optimized as a tree that would look at all the features and all the possible thresholds for each split. Did I forget something? No, I believe those, because those are the ones that are important to understand the random forest. Then we talked about the maximum depth that you can set that to avoid the tree splitting and splitting and splitting and ending up with these very small cells, right? So there are more parameters here to think about than in the k-nearest neighbors classifier we had before. Still, if you just talk about the decision tree, it means basically using these defaults. The defaults give you what people normally mean if they just use the term. It's like optimized over all the features, chosen the best threshold, trained to maximum depth until you have pure leaf nodes. Okay, just that so we are all on the same page again. And then we said that decision trees have all these nice properties. Here we have this comparison to support vector machines, which we're going to look at in the next lecture. And there are these really powerful classifiers that everybody uses, and decision trees are kind of regarded as a nice tool, and they have this white box property, but most people don't just train a decision tree. And the reason is, although it has all these nice green triangles here, that there's a weight on the predictive power, and this is most of the time the attribute we're most interested in. And I don't care whether my decision tree can handle mixed types or is robust to outliers in the input space if in the end the prediction performance is not as good as for the support vector machine. But then we saw in this data here, right, in this abalone data set, I trained just a decision tree and I got my score, and then I used bagging, and I said that is just an ensemble of decision trees, right? So I train multiple ones, in this case 100, and you see I get a real boost in performance here. And then I can get even a bit better with the random forest. And this is the power of ensemble learning, and hopefully you also got really motivated about this, like watching this video of the Netflix prize. I'm not going to show the video again. Instead, I have a short summary. So So I think these are the take-home messages from this video that we watched. If you weren't here last Tuesday, I think this video is fun. I put the PDFs of the slides online, has the link to the original video in the PDFs. It's on YouTube. I actually looked it up. It's made by Bell Labs, by AT&T, so where the team came from, right? So it might be slightly biased. Nevertheless, I think it takes the main insights from the Netflix prize and presents them in a fun way. The original video is also longer, so I showed you a cutted version of that one, if you want to go back and look at it. So the take-home messages from the video I showed, I think one was SVD rocks, right? Netflix prize, 1 million or something was the prize money, and the first method that everybody used and that gave these big improvements was SVD. And what they did is they used it for dimensionality reduction, also to impute missing values. And the block entry that they talked about from Simon Funk is actually still online. So you can dig it up if you want to and read what he did. It's also written in a fun way. So this is recommended reading, just if you're interested in what he did there. And I think the other take-home messages were that initially there was really great progress. Like after 1 year, everybody was blown away. The goal was to get 10% improvement over the initial prediction machine. And I think after the first year, they had 8% or something. So in the beginning, they really made great progress, and then everything slowed down. And they were fighting for every half percentage point. And the big choice that was made, basically all the teams went for ensembles in the end. I think all the leading teams had ensembles. And in the video, they said they averaged over, what, 800, I think? 800 different models that they trained. And this was actually a surprise and maybe also a bit of disappointment for the machine learning community, because we were hoping that there would be something really cool coming out of this, right? You have all these people being highly motivated, challenging data set. They can come up with a really cool new method, and instead it ends up just being averaged over tons of things that are out there. But it means ensemble methods are really cool to know about. So this is what we're going to talk about now. We have our single decision tree that does not really perform very well, but it's super fast, right? This is something you want in most all practical applications. If you want to build an ensemble, you want to build an ensemble of classifiers that are reasonably fast, because you need to train multiple classifiers of those, and you need, in the prediction, also ask every single classifier what he thinks the classes of the new data point, right? So you want something that is reasonably fast to go through your data set. But if we want to train multiple classifiers, we also need even more data. The more degrees of freedom your model has, the more things you try to fit, the more data points you want to have. And this is where bootstrapping comes in. And this is these are bootstraps. Actually, I had to look that up. I thought it's laces, the laces on boots, but it's not. It's like the guys you use to pull the boot on. And this is a story from Baron Münchhausen. And the story involves himself getting into a swamp, and he had to like pull himself up out of the swamp again. He did that by his own hair. And he not only pulled himself up, but his horse with him. And this is the idea of bootstrapping. It's to pull yourself out by your own bootstraps out of the swamp. Because what you do is you use the data you have and try to make it more, right? You're in the swamp, you don't have enough data points. You try to pull yourself out with all the means you just have there without external tools. So what does it mean? You have n data points, and from these n data points, you draw n times with replacement. So that means I end up with multiple sets, all the same size as the original data set. All of them have n data points, but because I sample with replacements, all of them are slightly different. Yeah? So that's the main idea. And then I use each of these bootstrap samples as their own, as one data set on its own. So here's a graphic explanation. So you have your data set, and you do the bootstrap replications of those, right? You just sample, and you get your bootstrap samples, and then you have your training sample from that. No, it's the other way around, I'm sorry. You have your training set here and your sample with replacement of that. And this gives you the single different training sets you can use later on. So this is really neat, right? I can just generate more data. Can I do cross-validation with this? Like I just generate one data, and that is my training data set, and then I generate the next data set, and that is my validation data. Then I generate another data set, and that is my test data. I like the shaking heads I see. Anybody cares to explain why? Why would you not do this? Wow. Yes. Yes. You have overlap. You're using the same data partly. You have overlap in those Bootstrap samples, right? We draw with replacement there. We draw n times with replacement. This is how we get to the n points again. But this also means that in our random samples, right, they're going to overlap. If I sample my data x1 and then I sample a data set x2, they're going to be data points that are in x1 and in x2. And to do real cross-validation, I don't want any data points in my validation or test set that I used to train the classifier. Yes?
But I can treat them, even they have the same value, but I still can treat them as different data. Even the same value appears twice, one in the training set, the other time in the validation set, but I still can treat them as different data points. Can we do?
Oh, they are the same. So the question is why you can't choose them as different data points,
I can still think of them
even though they are the same.
They
Yeah?
have the same value, but still different, two different.
So,
I know in reality they are the same, but can I treat them as, think of them as different?
so how would you justifying trading a data point that is like the same as two different ones?
I just assume that they are just from this real population. It just happened that they have the same value. Does it make sense what I'm talking about?
I'm not sure. Can you make, yeah, maybe talk afterwards. I just, at the moment, there doesn't come a practical problem to my mind where that would be likely happen, right? Like most of the time you want the data to fill your space somehow. So, but in general, as a rule, those Bootstrap samples are neat for training ensembles, but you need to do this real split before, split into training and test data, and do that before you start bootstrapping. So because Bootstrap has this overlap in data sets, and so I just put that explicit here in again, because what it turns out is, if you do the math, about 60% of the data points overlap. No, about 60% of the original data set are chosen in your Bootstrap sample. If you draw with the replacement, your n data points, you end up with a data set that has about 60% of the original data set in it. And the rest are replicas. So, and built upon this Bootstrap idea is the first ensemble method we're going to talk about. It's called bagging. And this is from Leo Brayman, and he was really great at building terms and creating these buzzwords. And bagging stands for bootstrap aggregating. And it's the closest idea maybe you can have about this. So you sample with replacement from your data set. This is the bootstrap. And then you train a classifier on each of these bootstrap samples, and then you just average them. Right? This is now the only randomness here between the different decision trees is not the parameters I talked about. It's just that they've all seen a slightly different version of the data. And that causes them to look slightly different, and that gives your ensemble more power. So because this is what happens. You train one decision tree, and you train another one. And maybe this one hasn't seen that data point. So it ends up with a slightly different decision line, right? Your decision boundary is slightly different. And you do this multiple times, and then you average over all of them. So to make this powerful, you want each decision tree to look different, right? Because if they all look the same in the beginning, then there's no gain really by averaging. So that's the main idea why an ensemble works so well. And there's this thing called the Bias-Variance Trade-off. And the idea is if this green line is my original source of the data, and then I can fit models, I generate points, right, randomly along this curve, and I inject some noise. And then I try to fit a new model to these noisy points. And ideally, what I would want is to take this green line, to get this green line again, right? So this is a simulation example, just to show you what is going on. I know the source that generated the data. It's this green line. I sample points with noise around this and fit a model. And it's, again, as with the k and k nearest neighbors, as with the depth of the decision tree, I have a parameter that regulates the smoothness of my model. And here you can see if I basically put a lot of regularization in, and I get a very smooth model here, I have the problem that I don't have enough flexibility to actually fit to the original source of the data. On the other hand, if I allow it a lot of freedom here, because there's noise in the data points I fit to, I get these very ziggy-zaggy lines. So if I would only consider one of those, right, I'd still be a far cry off of that original curve. But now I generate a lot of those and I average over them. What you see is now I can actually fit to my green line. So the idea behind the ensembles is that I can reduce the variance without introducing this bias. Normally, if you want to reduce the variance in your model, because you want to avoid overfitting, you have to introduce this form of bias. You have to introduce some form of smoothing. And hopefully what this averaging does for you gets rid of variance without introducing bias. Yeah, I'm actually going to skip over this. So decision trees, one of the negative points of decision trees actually is that they can look very different if you just have slight variations in the data. And this negative point is what Leo Brayman used as their strength. Because each Bootstrap sample looks slightly different, you get different decision trees, you can average them, you get your nice boundary. And this is an example here from the Hasty book. So this is just one decision tree here. This is test error, so slower is better. And here's the number of Bootstrap samples you have. So it's the number of trees you trained, and you average over. You can see here's the performance of just one decision tree. And if you instead use an ensemble, you see this error goes down pretty fast. And then this is typically that you get this slightly jiggy-jaggy performance, but you kind of converge to one value. I've seen this a lot this way. And what you see here also, he compares consensus versus probability. Does someone remember what that was about? If you do not have pure leaves in the end, there are two versions to make a prediction. Okay, maybe nobody remembers that one. If you have in your leaf 4 data points that are red and 2 data points that are green, then you can just go by majority vote, right? And you always say red, because 4 data points in the leaf are red, so it always gets the red class. Or you can assign probabilities, right? Because there are also 2 green data points, so it's not 100% red. So this is what he means here. Consensus is if you just take the majority vote, I guess, and probability is taking into account that your nodes are not pure. And you can see this has this nicer behavior here with the probabilities, but it doesn't really make, at least in this example, that much of a difference in the overall performance if you use enough trees in your ensemble. So we said bagging reduces the variance, and this means it reduces overfitting, right? You've seen these ziggy-zaggy lines. This means they fit the noise in the data points. We got rid of the noise part by averaging over many of those. And normally it uses one type of classifier. It doesn't have to be decision trees, but most people use decision trees just because they're really fast and you can have a lot of them. But there is nothing hindering you in principle to do this with support vector machines. It's just going to take a lot of time. And you need to find a way to make them different, right? So the decision trees are popular as the choice. Bagging doesn't help with linear models, though. Why not? A linear model just has a straight line as a decision boundary. Has help. Yeah, there's not enough variance to begin with. Like, if you don't have the problem of overfitting, if your classifier is so restricted in the first place, there's not that much to gain. So support vector machines maybe not the best of choice. Easy to parallelize, that is very neat if you have to do a lot of computations. There's nothing that links these three together except for the average in the very end. So in principle, you could use even a computer cluster, and if each node just train one tree, and for each data point query one tree, right? And then you just need to average over them all in the end. So it's very easy to parallelize. Okay, questions about bagging? Yeah? So the question is why it uses normally one type of classifier. I think traditionally it's just because it's the decision trees and they're so fast, there's nothing preventing you from using different ones. Like really. It's as in Netflix, they've basically done the different models, right? The only thing is you want to have this variability between the classifiers so that you can actually have a gain out of the average. And I believe in the Netflix price, for example, they call it blending, and I think they weighted the different classifiers, right? If they're all the same type, then it's a no-brainer. They basically all have the same predictive power, most probably, and you don't have to weight them, you just take the average. If I have one in their decision tree and one k-nearest neighbors, you have to think about how much each should contribute maybe to the average. So I would put a bit more effort and thinking into it if you want to like use bagging with different classifiers. It's a no-brainer if they're all the same, but it's totally possible. Okay, the question is what they used in the Netflix price. I'm not entirely sure. They call it blending. I believe most probably they didn't bootstrap. If at all, they might have subsampled because the data set was so large. And they also had very different classifiers, right? In the video, they said that in the end, they took things into account, like on which day the user rated it, because maybe on Mondays, you're more grumpy than on Fridays. And so I believe that that already introduced different decision boundaries in the different models they had. That was a whole different level, I think. It was for sure more than just bagging. Oh, more question? Yeah?
With the linear models, wouldn't bagging basically help you find the best margin? Would give you better performance?
Yeah, maybe. Yeah, could do that. It's just, yeah, exactly. I was just thinking, yeah, but then you would just use the support vector machine and yeah, I guess. Okay, Kinect. Yes? Oh, sorry. Some cases where bagging is highly recommended. I actually think most of the time now I would use a random forest, which we're going to talk about now. It was like the next step. So historically, it was decision trees first, I think. Then people used bagging, and then they went over to the random forest, which are very similar, you're going to see. They just try to make the trees even more, they introduced this randomness to make the trees even differ more one of the other. And that gave a bit of an additional boost. But these, this is why, so random forest we're going to do today, and the next one next lecture we're going to do support vector machines. And I believe these are still the two strongest classifiers for nearly all problems out there. Like if you would tell me you're only allowed to teach 2 classifiers, those are the 2 I would choose. Because there are still a lot of biology, physics, chemistry papers out there who use these 2 classifiers. Yeah. They're like from the off-the-shelf ones, I think also the most popular ones at the moment. And then comes deep learning. We're going to talk about that in the very last lecture a bit. Okay, random forests. Who of you owns an Xbox? Very, very shy. Oh, at least some people. I had a lecture before where I asked, and I think nobody dared to say it because I was like, come on, guys, at least a bit of fun must be in your lives. So, or maybe it's all PlayStation fans. I don't know. So Xbox with the Kinect, and this actually uses a random forest. This was big news, not only because it's a great motivational example for lectures that I give, it's also always nice to see if something that was used in research only makes it into products. For me, that is always like the ultimate proof that this thing works and works in real life applications. And so the Kinect, first of all, again, is an example that we want to measure more than the human needs. Like computers are still dumb, right? If you want to estimate the pose of one of your colleagues, all you need to do is look at them. And I'm pretty sure you could even estimate the pose if you would close one eye. So if I only show you a 2D picture of that person, you still would be fine. The Kinect, however, has the RGB camera, but it also has a 3D depth sensor. And that was a big revolution because it was the first time, I believe, that this hardware was made so cheap that you could put it into a commercial everyday product. So the sensor has this RGB image, the depth image, and the audio stream. And there is a random forest in there that does the body part recognition, right? Because when you have your video stream and your image, in order to actually play a computer game, you need to estimate where the hands are, right? And whether the player just really hit that ball or not with his hand. So you need to estimate a body skeleton and the joint positions in 3D. And Jamie Schotten did this at Microsoft Research, and you can look at the paper, it's online. And he did this with a random forest. So the random forest in there estimates body parts from this initial depth RGB input. And if you've ever played on an Xbox, it's working quite reliably, and it's working pretty fast. Okay, how is it working? So it builds upon the idea of bagging that I already said. And each tree is, again, built from a Bootstrap sample. So this idea carried over. You have your data and your sample with replacement. But now we induced additional randomness by only choosing random feature subsets for each tree. So this was this mbest parameter that I talked about. So then in the end, I have a bagging, right? A bagging approach that has this additional parameter. All trees are fully grown, and I don't have any pruning. What are the only 2 parameters that you should think about if you want to do cross-validation? One I've already said. We've talked about both, more or less. Yes?
One is the number of features.
Yes. So let me. What is the number of features? Oh, and I put the answers down. Okay. And the other one is written there. Number of trees. Oh, you actually didn't see that. Haha, next time I'm not going to say it. So if you want to train a random forest, that's another very nice part. And it's actually sets it apart even from a support vector machine. It's called an off-the-shelf classifier. Most of the time, you don't even need to bother much about these parameters. Take about 300, 400 trees, and you normally find, because you're way out of the range where it converges to this one performance line, and the number of features has a default in there, and that is the square root of the number of features you have. And in most cases, that actually works well. Yeah?
So number of trees and the number of bootstrap samples, that's the same thing, right?
Yes, each tree gets a bootstrap sample, and the size of the sample is always the size of your original data set. Yes? Yes?
Just to verify on number of features, that's the number of features that's chosen at each iteration of creating the tree.
Yes.
But it means that over the course of building the tree over all the different splits that you make, all the different features could be used at some point.
Yes.
Is that not right?
Yes, exactly. So the question was just for the extension school students. I forget repeating stuff. So at each split, you look at this number of random at this number of random features that builds a subset of your whole feature set. And so at each split, you redecide. So in the end, when you traverse the whole tree, if you have enough splits, you've actually looked at every feature in there. Yes. There's, yeah? Yeah, so the question is whether we could also vary the criterion for splitting. I've not seen that done, but I guess you could. I don't know how much randomness that would actually introduce, like how different they are if you choose one over the other. What I've seen instead, there's also this notion of extremely randomized forests. So people really went with this idea to introduce more and more randomness. And the most extreme version I've seen doesn't really learn anything. It's just all randomly sampled. At each split, it chooses a random subset of the features, random thresholds, and randomly takes one of those. And this is called extremely randomized forests, and they still work. Yeah, that also blew me away. So the error rate. Now, this is why you should worry a bit about the number of features you want to split on. So if you have correlation between trees, that is not so good, right? You want them to be different. So higher correlation is worse. Can you see that? If your trees are not that different, then the averaging doesn't give you as much improvement as you maybe want to. But on the other hand, you want the single trees to be quite strong, right? That is an argument against randomizing too much. You want each tree in there to actually learn something. So there's a trade-off here. Oh, yeah, so I basically just answered my question again. I should look at my slides before I explain things. So the correlation higher is worse because you don't have that much randomness in your ensemble. You have trees that look the same, right? You can think about if I wouldn't induce any randomness, and each decision tree would look the same, they would be perfectly correlated, and the output would be the same as only one decision tree, right? If you take that to the extreme, that idea. So I want them to look different. But on the other hand, if I make them so different that they all don't learn anymore from the data, then averaging is not going to help me to actually get a good result. So, and on that notion also, if I increase the number of features I look at each split, then I increase the correlation, but on the other hand, I make each tree stronger. So that is the parameter that regulates this behavior. Right? Because that is the point where we induced additional randomness. The bootstrap sample is basically fixed. We want to change that. So the number of features for each split, here is the point where we induced randomness to make them look more different. Are there questions for this? I think if you really understood this, then you understand what the random forest is all about and what this version of ensemble learning is about. Okay, there are some really neat and nice things about the random forest, which is mainly, this is not something you couldn't do with other ensembles as well. It's just Leo Brayman defined the random forest to have these additional features, and so most of the packages out there are going to give you options to calculate these. Especially good is the R package for random forest. Scikit-learn has also one. It lacks a few of the features, but it's still, I think we're going to use it in the homework. So there's something called the out-of-bag error. And what he claims is that this is an inbuilt version of computing the test error. That's very neat, right? You don't have to put a data set aside in the beginning. On the other hand, you have to be extremely careful because ISET never ever fit on the training data, but we want to train the random forest somehow. So how does that work? You take your Bootstrap sample, and we said the Bootstrap sample covers about 60% of your original data points. It was a bit more than 60%, so I have about 30% that I didn't use. And the idea is that you can use these 30% as points to estimate a test error. Now, but if I have all the single Bootstrap samples, right, and I make 500 of those, in the end, they most probably covered all of my initial training data. But for each single Bootstrap sample, this rule holds. So what I do is for each single tree, not for the whole forest, for each single tree, I have my Bootstrap sample, and I have the rest, the leftover points from my training sample that did not make it into that particular Bootstrap sample. And those I can use to estimate the test performance for that single tree. Again, not for the whole forest, just for that single tree. So the idea is that you can do that for each single tree, and that can give you an idea of the overall performance of the forest, because you know how strong the single trees in there are. Still, I would not count this out-of-bag error as test error. Like if you plot them one against the other, most of the time this tends to be a bit too positive because it's not a true test error. So, yeah, Christian? Okay, the question, if I got it right, is how could that work? It's not really giving you a test error if you do that for the single trees. That's what you say, right? So yes, that's what I believe too. To really get the test performance, you have to set aside a test set in the beginning. But he claims that you can compute this out-of-bag error, and indeed you can, and a lot of the packages give you that option. And what it's nice for still, what you can use it for example, is validation. You can, for example, tune the number of trees you use. What I normally do is I plot the out-of-bag error against the number of trees, and then you can see exactly nearly that line that we've seen for the bagging example. Like your error reduces, and then it gets to the ziggy-zaggy line on basically the same performance level. And this is nice, so you can choose the cutoff of how many trees you use. But I would not report the out-of-bag error as the actual test performance, predictive performance of the random forest ensemble. So he claims that you can do this, that the out-of-bag error actually gives you the error for the whole random forest. There have been papers published afterwards that say it's slightly too positive. And I think it's a neat tool for things like estimating how many trees you could have in your ensemble. So here's a version how this works. So you have your initial data points, right? You sample from those. You have your Bootstrap sample. You train your tree. And then you use the unused data points that were not in your Bootstrap sample and get the test performance for this single tree, not for the whole forest. So I already said it can be too optimistic. It's measured during training. That's neat because you just kind of get it for free. Prediction with the single trees is fairly fast. So normally you don't lose that much computation time if you tell it to please give you the error score. Variable importance is another neat thing. We've already seen that for a single tree, right? We said that it can give you a measure on how important each of the features is by looking at the gain in purity, if you remember that. So it can rank the features according to how gain the split gave to the purity measure. And here now he uses the out-of-bag samples again. And what you do is you use the samples that were not in your Bootstrap sample, and you predict the class for these samples, right? So that's as in the error measurement. But now you randomly permute the values of one feature. So you scramble that one feature and make it useless. And you predict the class again. And then you see how many errors you do now. And that gives you a measure on how important that feature is to discriminate the classes. That's the idea here. So what that means is, this is from the very introductory lecture on machine learning, right? We had our apples and oranges and measured were shape and color, right? And the shape is so similar that it doesn't give you much information, and the color is different. So this is the actual feature you want to use, right? So if my decision boundary is here from the split from my decision tree, and I scramble the shape feature, nothing happens, right? If I scramble only this feature, only the shape feature, the color stays the same. So what that means is this point here would land anywhere on this line here that is parallel to shape. Maybe these 2 points here switch. So this guy goes here, and this guy goes up here. So I scramble the points. I scramble the feature values of those points. And what's happening in the feature space is they all go up and down here and change positions, but not left and right. Right? Because I only scramble one feature, the shape. And because this didn't give anything in the first place, scrambling this doesn't change anything on my error rate. Right? None of these points, because this split is not doing anything anyways. And if I have the real split here between the ones, if I scramble here, I still get my nice performance. If I scramble here, I still get my nice performance. If I scramble the color, I'm in trouble. Right? So this is how he measures feature importance here. Directly estimated from the data, not just the gain at each split. And then the other version is to, again, just use the split criterion. So that was the Gini impurity that we also already talked about in the decision tree. These are decision trees, so you can do the same for the random forest. And this is a comparison that Hasty has in this book on what this could look like. And I don't remember him really recommending one method over the other, which I think is a bummer, because they are different. So you can see here that the Gini gain, right, discriminates much more, whereas this is a more uniform distribution over your features. And I actually don't know which one to trust more. I think I would go with most probably with the random sample, just doing this out of this notion that it's estimated from the data. But I could not tell you right now that one is really better than the other. You can also do both and compare, right? Some, like the very most important, I don't know what this was actually about, but the most important feature, yeah, are kind of the same. Not even totally. No, the most important feature is the same. And then place 2 and 3 are, here it says tree and remove, and here it's remove. So maybe do both and look up which ones land in the best 5% or something. So and another thing you can do is measure proximity between data points. This is something that we already used for k-nearest neighbors and things. We had a measure on how close 2 data points are together. And the measure we always used was just Euclidean distance, and I just didn't talk about it, right? So we just assumed that is the distance to use. But maybe you have different data, and this distance actually doesn't make sense. So this is the way you could tune, for example, also a k-nearest neighbor classifier, come up with a different distance measure. A random forest can also estimate the distance between data points. And what it does is it has an n times n matrix, so it's huge, right? It's the number of data points times the number of data points, and it gives you the proximity between each pair of your data points. And what you do is you classify the complete data set for each tree, and if the points end up in the same leaf, then you increase their proximity because they're close to each other in the sense that they landed in the same cell in the feature space. And this is an example of what this looks like. And they said this is typical. If you have points here, you get these star shapes out. And things that are on the pointy ends are way secure somewhere in the feature space, far away from the decision boundary, right? Here's my 1, and the 6 is up here. Oh, the 4 actually doesn't look that secure, but it's up here. And then things that are more in the middle area here, like the 3, those are close to the decision boundary. Maybe this counts as to the middle. But the ones wide out on these arms normally are further away from the decision boundary from the random forest. Okay, another thing that you can just do with this subsampling, this is a problem I'm going to talk about later again, it's unbalanced classes. If you encounter unbalanced classes, and a lot of applied problems actually do have unbalanced classes, you need to think about how to handle those. This accounts basically for every classifier out there. What do I mean by that? You have 10,000 data points, and only 2,000 are class A, and 8,000 are class B. Then you need to think how to make the classifier realize that those 2,000 points in class A are actually important to you. And one version to handle this is to oversample, right? We drew with the replacement. For our Bootstrap sample, there's nothing hindering us from actually just keeping on sampling until we have 2 data sets that are the same size. And the other option is to downsample the majority class. And I found a paper on this, and they claim that it normally gives better results if you subsample, which I found surprising because then you use less information from your majority class. I thought this is normally not something I would want. Now, the random forest actually gives you a nice solution to this problem. You can subsample for each tree. And this is what I normally then just do. Like you have your majority class and your minority class, and you subsample for each of the trees. So each of the trees is balanced now in its training, but in the end, the whole forest has seen all the samples from the majority class. So to summarize, it's similar to bagging, and it's also easy to parallelize, right? You again have all the trees working in parallel, and you have these neat functions normally in the packages, like the out-of-bag error, the feature importance measure, and this proximity estimation. You have to look in some of the packages, they are off by default because it's additional computation that you need to do, so you need to put a true somewhere in there to get those measurements out. Okay, that's about the random forest. I wanted to go into performance evaluation now. Any questions further about the random forest? Yeah? Like in the random forest result in the end, you literally ask each tree which class it thinks, and then you average over those. So if 3 say yes and 3 are no, say no, you're in trouble. Because it's just 0.5, but it's like, what? Yeah, you average really the prediction results in the end. You query each tree as if it would stand alone on the wide meadow, and in the end, you just average over all of the responses you got. No more questions? Okay, cool. So we talked about this briefly already. Just a short recap, we said if I want to evaluate the performance of a classifier, I can look at the true positives. This is if the true label of my class is 1, let's say foreground, and the predicted label is also 1. So I say it's foreground or face, for example, and the classifier says it's a face, then it's a true positive. If it's not a phase and the classifier also says it's not a phase, it's a true negative. And then I have the two errors. Either it's not a phase and the classifier actually says it would be one, then I have a false positive, or it is a phase and the classifier doesn't find it, then I have a false negative. So I have, in a binary classification problem, I have these 4 options of outcomes. And there are 2 measures for this. One is the true positive rate. So if you look at the confusion matrix here, what this does is it looks at the whole number of samples that actually are in the positive class, the foreground class. So these are all the phases in my data set. And then I look how many of those phases were actually found. So it's the number of true positives divided by the total number of points I have in that class. And then I also have the false positive rate here. And it's the same just for the false positives. So it's the false positive divided by the whole number of negative samples or of background samples. So I have my true positive rate and my false positive rate. And most of the time, those have a trade-off. And what you do is you plot those in a receiver operator characteristics. So this is the true positive rate plotted against the false positive rate. So what I want is to go to the upper left corner. That is the perfect classifier. If you look, this means my true positive rate here is 1, which means I have found all the true positive examples from all the data points that are foreground. I have found them all. And my false positive rate is 0. So I haven't found any phases that actually are not phases. Then I'm doing really well. And people like this visualization because this is the random choice line. So you can basically look at your performance, and if you're here, you don't like your classifier that much. And if you're up here, then you're fairly happy. What happens if you're there? That's bad, yeah. That means you did a lot of mistakes. What are you going to do if your point ends up there? What? Flip the answer. Yes, exactly. Right? If a classifier does this, you flip the answer it gives, and you're up here. Right? You can just mirror on that line. So you can't really go down here. Random choice is the worst thing a classifier can do. So you flip your answer, and you actually had a pretty good classifier. So there's another measure, which is called precision recall. Recall is actually just the true positive rate. So again, true positives divided by these guys. And now, instead of looking at the second row, I look at this column for precision. So it's, again, only caring about the true positives, and then dividing that by the number of labels that the classifier said would be class 1. Can somebody think why this is beneficial? That's a bit wide out. What do I not look at with this measure? With the true positive and false positive rate, I'm looking into every cell of the confusion matrix. Here I'm missing one. Which one am I missing? Yes, I'm not looking at the true negative rate. And the reason for that is, I think that it's actually a feature, because if you have an unbalanced problem and you have a majority background class, then your true negative rate can be fairly high, which means you're doing a lot of things right, but it's easy to do them right because you have so many sample points in that class. And what happens is that your receiver operator characteristic looks really positive. You're almost out there. But that's because I think it's kind of a bit maybe cheating, because you're giving this impression that you have a classifier that performs really well. But what just happens is that your false positive rate here in the denominator has the true negatives, and those are really high because you have so many points in there. Right? So you would have to change this rate a lot. Right? You have to get really, really bad to make an impact here and get that curve down. So what that means is, so first here, precision recall by itself. So now in precision recall, you want to be in the upper right corner. And you plot these curves normally by varying a parameter. And what you can think about if you have a detection problem, let's say face detection, recall is how many of the faces did I actually find? How many of the faces that are in there did I actually find? Not how many, but what is the rate, right? What is the probability of a face in the data set that I actually find it? And then precision is when I say something is a face, what is the probability that it indeed is a face? And I think you can really see the trade-off here. I can have a very, very high recall and a very lousy precision. What do? Everything is a face, yeah. If I just go out there and say everything is a face, I have perfect recall, right? I get every face in my data set. But my precision is really crappy because the likelihood that the probability that something where I say it's a face actually is a face is fairly small because I'm just saying face all the time. And this is the other way around, right? This is I say nothing is a face. Then I have no recall at all, but I have very good precision. And in a lot of, for example, in biology, we do synapse detection, and the biologists actually are fine with a more or less crappy precision as long as we can guarantee that all the synapses are found, because they can proofread later. It's easier for them if we select points of interest and they can say yes, yes, no, no. If we would have something in between here and say, okay, we got fewer recall, but our precision for that matter got really good, but then they have to look at all the data again, right? And see and look for the synapses we might have missed. So this trade-off is important in a lot of applications because it depends what really optimal means for you, because most of the times you can't get to the upper right corner. And which trade-off of this is actually beneficial for you depends on your application. So with these two curves, for example, without knowing what the application is, I wouldn't say one is better than the other, because they're similar away from the upper right corner, right? So, and this is a paper that compares precision and recall in ROC curves. And what they basically found out is it's OK to compare algorithms with either. If an algorithm performs better on a ROC curve, it's also compare better on the precision recall curve. It's just on ROC curves, it might look more positive than actually on the precision recall curve. You see this here, right? The dotted guy is maybe better in this area. It's also better in this area. But here it looks like the overall performance is very good. Look how close I am to the upper left corner. Whereas if I look here, there's a lot of room for improvement, right? So, and then there are, of course, cases where I actually don't want two measures, but I only want one, right? And in this case, you can take the weighted average of precision and recall, the harmonic average. So this is called the F measure. And in most cases, beta here is 1, so it's F1 measure. So that would mean you just have precision times recall divided by precision plus recall. I missed a 2 in there. This becomes 2. Sorry. 2 times precision and recall divided by precision plus recall. And this is an average that kind of encodes how close you are to this upper right corner. This is useful, for example, if you want to plot performance against a parameter, really. How you get these curves normally is you vary a parameter, right? And then you vary this along these curves. For example, if I have a random forest, I could not just take the majority vote, but I could actually take all the votes out there and vary the threshold. Like how sure does the random forest have to be for something to be a synapse, right? And then I get one of these curves here. OK. I have boosting, cascade, classifiers, and face detection left, or we could just leave it here. Who wants to learn something about boosting? You don't have to. I mean this. Hand signals. Who wants to get out of here? I'm not going to be mean and say no. Who wants to actually see boosting and the cascade classifier? Oh, there actually are people. $45. How about you guys who want to leave, pack really quietly, because I promise what I'm going to talk to about now is not going to be in any of the homeworks. So it's fine. I'm just going to talk about the rest for the others who just want to stay for fun. Like, I'm going to give you a bit of time. Okay, so many people are staying. Cool. Or they're just not fast enough with packing. I just feel the topics already were a lot. So I'm just going to talk about the whole idea of boosting. And it's also kind of an ensemble method, but just does more than just averaging. What you do is you weigh your classifiers. This means you train one, you look at the result, you make corrections. You train the next one, you look at the result, you make corrections. And then you also average them with weights. Like you say, one performed really well. I want to put a high weight on the vote of that classifier. The other one maybe did not perform that well, so it gets less of a weight for the actual results. So this is the idea. I draw one decision boundary. And then I look at the classification performance. And a few of the points are going to be mistakes. So you see this decision boundary is here, and it's going to separate blue and red, and it made mistakes here. So what I do now is I put a really high weight on these points and say, for the next classifier that I'm going to train, please pay attention, especially to these points, and get those right. So what's going to happen is I'm going to get a different decision boundary the next time. So instead of inducing this randomness thing, I'm actually looking at the performance of the previous classifier and try to correct the mistakes it made. And this is just summarizing what I said before. The astounding thing about this, most of the time, AdaBoost also works with decision stumps even. So it's only a tree that only does one split. This means one axis-aligned split on one feature. That's your whole classifier. That's called a decision stump. It's not even a tree, it's just the first stump. So in real life, when you have this application, it wouldn't be a diagonal line. Any slanted version would be an axis-aligned split that is allowed. And you can see here, this is a single decision stump, so they're really dumb, right? And then this is a normal decision tree. And although the boosting only uses these guys here that do not perform that well, if I go over a lot of iterations, you see I can really get my error down. And this is a video. How this can look in real life, and it's not going to have any sound. So here you see the data points that I have, and you see these splits here are only axis aligned. It's really just decision stumps. And nevertheless, by averaging over them, over all the iterations, can actually build a decision boundary that separates these two data sets. And this, of course, is also very fast. Yeah? The question is on which data set I train each of these models. For this, it's the same data set. There's no randomness or bootstrapping in there. But you reweight the samples. So this is why you get different results. You look at the errors the previous classifier made. You don't train them in parallel. You train one, and then you look at the mistakes it made, and then you put an emphasis on those and say the next classifier better gets those right. And then you train the next one that gets other samples wrong, and so you iterate further on. All of them. Yeah, I believe. So the fun fact about AdaBoost is that it was introduced in 1995, and it worked really cool, and nobody understood why. everybody was puzzled, right? Because it's like these decision stumps that don't really perform that well on their own, right? And they just had this hacky idea of reweighting the samples and got such astonishingly good results. And it took over 5 years until Friedman actually came up with a theoretical explanation what ADA boost might do. And in his book, he writes he still has open questions about it. So I think it's a very nice example where intuition can help you build a classifier that performs really well in practice, even if not even the experts understand why. So, and this cascade classifier is in here because I believe it's still the one used on your mobile phones. So the ensemble methods are strong, but the prediction is slow, can be slow, right? Because you need like 300, 400 trees. If you have something like a mobile phone or camera and want to do face detection, that most probably is too slow. So the solution is we want to make the prediction very fast. And the idea is to build a cascade classifier. And this was the first face detection classifier that actually made it into the real world, into commercial products that was fast and reliable. So the idea is you have sub-windows, and you now, instead of querying all the classifiers at once, you query them one after the other. And the idea is you don't train them to be very good in the overall performance, you train them to reject. So the first classifier is just very good at detecting something that is not a face. And it's going to let a lot of non-faces still through. It's just for rejection, for filtering the very easy cases where you can already say this is not a face. And the gain you have is that for the next classifiers, don't even have to look at it anymore. If the first classifier said this for sure is not a face, then the others don't even bother to look further at that image patch. And only if this guy says, yes, it's a face, then the next guy looks at it and says, yes, I also believe it's a face, and the next guy looks at it. And because most pixels in an image actually are not faces, that makes it so fast. And if you do the math, what comes out is, if you have a 10-stage classifier, and you want to look at the performance, then your detection rate, you want a detection rate of 0.9, then you need a detection rate of 0.99 per stage. So each of the classifiers is only allowed to miss 1% of the faces. That is a very high recall that you want here, right? You want to catch all the faces. But the good news is you don't bother that much about the precision. So in your precision recall curve, you'll find very high recall, very poor precision. You're somewhere down there. And because you multiply them with a high false positive rate, because they're in this chain, in this cascade arrangement. If you multiply them, even if you have a very, very high false positive rate, if a sample made it through the whole cascade and you multiply them all, you actually have a very low false positive rate at the end. And this is a video how this can work in practice. So this is the slow version, right? The real thing goes like snap. These are the types of features it looks at. So it's quite kind of simple features. Also here, emphasis on computation time. These rectangular features are very easy to compute. And what you can think about is it's looking at difference and contrast, right? If you have a nose and eyes, then you have two dark patches and a white stripe in the middle. So this is the type kind of features it looks at. And you can see that it goes very fast over some areas here of the picture that are not a face. And these are rejected at very early levels of the cascade. So the classifier doesn't even bother looking anymore in the deeper stages. And now we're getting to the face and to the eyes, and it's going to slow down, right? And although it's still not saying it's a face, it took it a lot longer to actually reject that frame as not being a face. I believe now, are we there? Yeah, now it's like really going in there, and you see now it's imprinting these frames. And this says it detected a face, so the whole cascade went through. And you get multiple of these, and then in the paper they described how they aggregate these detected frames into one face detection. So this is the Viola-Jones face detector. And the paper is quite nice to read. It's not that complicated. But it made a high impact because it was so fast. So that doesn't happen very often, that somebody comes up with an idea that works that reliable and is then even computationally efficient. So there's Lena. Somebody seen that picture before? You're going to see this a lot in image processing classes, especially if it's about compression, because she has this nice feather thing there. Image processing people love her. This is actually a Playboy centerfold. That was used, I always forget the university, but they say it was close to the paper deadline. They didn't know what to do, and they needed an image to show that their algorithm works well, and they cut it out. So you can look and Google her. She's called Lena, and you can see the whole image. Sorry, I didn't understand you. Yes. Yes. The question was, this is only faster if you have very unbalanced points. Well, I mean, then the gain is the largest, right? Because the more you can reject right at the beginning, the faster you go. Yeah. If the classes were balanced, you would still be faster, right? Maybe, because those, and maybe it depends on how much stages in your cascade you need to actually classify the foreground pixels, right? You still would go very fast over the negative ones. So then the question is, how long does it take you to classify the positive ones? Is the speed gain you have from the negative ones enough if you would compare it to random forest that runs on every pixel, I guess. But yes, I mean, face detection is a classical example of highly unbalanced, right? If you look, even now that I look at a lecture hall, I have a lot more, if I would take a picture, I have a lot more pixels that are not face than face. I guess a highly packed football stadium is one of the rare cases where you would actually have more faces. Okay, that was it. That was the Viola face detector. So the random forest is in your Kinect, and the Viola Jones face detector is in your camera, most probably.